This word is orbital. It is about how electrons orbit round the nucleus in an atom. Now, we used to think, Rutherford's time, that the electron went round like the Earth goes round the Sun. But in fact, you can't treat it like that, because the electron is all over the place, behaves like a wave. You can't tell exactly where it is, but you can tell the approximate volume that it occupies. And the volume has a really funny shape. And they're different shapes that are important for different atoms. In fact, it's these different shapes that give the periodic table its whole structure. The simplest shape is called an s orbital, sphere. Then there are three orbitals called p orbitals, which look like this, which have two blobs with a nucleus in the middle. One pointing upwards, one pointing towards you, and the third one, if I don't drop it, pointing out of the door. The third.
Hybrid orbitals are formed by a mixing of the hydrogen-like s, p, and d orbitals that characterize a free atom. The three p orbitals are directed along the x, y, and z axes.
Mixing an s orbital with one of the p orbitals generates two equivalent sp hybrid orbitals. Note that the number of hybrid orbitals is equal to the number of atomic orbitals that are hybridized. The set of two sp hybrid orbitals has a linear arrangement. The angle between the orbitals is 180 degrees.
When we mix an s and a px orbital, we produce two hybrid orbitals called sp pointed in opposite directions along the x-axis.
Putting these ideas together, we can imagine the hybridization process for BeCl2 is something like this. The isolated beryllium atom, with its filled 2s and empty 2p's, is shown with the small box diagram above. The chlorines have three 3p orbitals, but will fade out the ones that are not involved in bonding. In the molecule, beryllium has undergone sp hybridization. The half-filled sp hybrid orbitals overlap the half-filled chlorine orbitals to form two BeCl covalent bonds that are 180 degrees apart.
Mixing an s orbital with two of the p orbitals generates three equivalent sp2 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybridized. The set of three sp2 hybrid orbitals has a trigonal planar arrangement. The angles between the orbitals are 120 degrees.
Mixing of an s with the px and py orbitals produces three equivalent hybrid orbitals in the xy plane. We call these sp2 hybrid orbitals. Notice that the hybrid orbitals have major lobes which contain most of the electron density in the orbital. These are used in bonding to other atoms.
Consider the benzene molecule C6H6. Each carbon atom is sp2 hybridized and forms sigma bonds with two adjacent carbon atoms and another sigma bond with a hydrogen atom. The six 2pz orbitals form pi bonds. Electrons in these orbitals are actually free to move around the entire benzene ring.
Mixing an s orbital with the three p orbitals generates four equivalent sp3 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybrid. The set of four sp3 hybrid orbitals has a tetrahedral arrangement. The angles between the orbitals are 109.5 degrees.
Mixing of the s with all three p orbitals results in formation of 4 equivalent sp3 hybrid orbitals, directed toward the apices of a tetrahedron.
The model describes bonding in methane this way. In the molecule, the carbon's 4 sp3 hybrid orbitals point to the corners of a tetrahedron. The H orbitals overlap them to form 4 CH bonds that are 109.5 degrees.